Welcome to the third lecture of two-phase flow and heat transfer. In this lecture, we will be discussing about homogeneous model. So, at the end of this lecture, you will be understanding applicability of homogeneous model, what are the basic assumption of this homogeneous model, that also we will be understanding in this one. We will be calculating the pressure drop inside a pipeline having homogeneous flow. Also, we will be seeing that homogeneous flow in the presence of phase change, and at the end of this lecture we will be also practicing one sum where we will be finding out pressure drop in case of homogeneous flow. Now, to give you a basic outline of this homogeneous flow, here I have shown a figure where you can find out that lots of bubbles of gaseous phase are actually homogeneously dispersed in the pipeline in the liquid vicinity. So, here we will be calling the liquid velocity as UF and gaseous bubble velocity as UG. Now, based on the assumption of homogeneous flow, we consider UG is equals to UF. So, that means in homogeneous flow we consider the gaseous phase velocity is equivalent to your liquid phase velocity. So, here we write down this velocity as UH, H signifies homogeneous model. So, you will be finding out UG is equals to UF is equals to UH. This type of flow regime is very common for bubbly flow situation, wispy annular flow situation and so on. Next, as it is homogeneous flow, first we need to understand what are the different properties we can have for homogeneous phase. So, here first one I have shown you as density. So, density rho h for the homogeneous flow can be written as alpha into rho g plus of 1 minus alpha into rho f. So, let us see how that can be proved. So, we know that from continuity equation W total flow rate is equals to W g plus W f, right. Now, in case of homogeneous flow, this W can be written as A UH into rho h. So, rho h is the homogeneous density and UH is the homogeneous velocity. On the other hand, Wg can be written as Ag, Ug and rho g from continuity equation. In a similar fashion, Wf can be written as Af, Uf and rho f. Now, as we know from homogeneous model that UH is equals to Ug is equals to Uf, UH which is homogeneous velocity is equals to Ug and Uf. So, this U can be cancelled from both the sides. So, I will be finding out rho h is equals to Ag by A into rho g plus Af by A into rho f. Now, we know Ag by A is nothing but our void fraction alpha. So, we can write down this is alpha into rho g, and similarly Af by A, this is nothing but 1 minus alpha into rho f. So, we get that rho h is actually alpha rho g plus 1 minus alpha into rho f, the equation whatever I have shown you over here. In a similar fashion, if you go from area side, so total area of the pipeline is occupied by the gaseous phase and liquid phase. So, I can write down A is equals to Ag plus Af. So, A I can write down W by UH into rho h from continuity equation. In a similar fashion, Ag can be written as Wg by Ug into rho g, and subsequently Af can be written as Wf by Uf into rho f. Okay. So, here once again by taking the homogeneous assumption, the velocities can be cancelled, UH equals to Ug is equals to Uf. So, we can write down 1 by rho h is equals to Wg by W into 1 by rho g plus Wf by W into 1 by rho f, right. Now, we know Wg by W from thermodynamics, this can be called as x, okay, and Wf by W can be called as 1 minus x, right. So, using this I can write down 1 by rho h is equals to x by rho g plus 1 minus x by rho f. So, homogeneous property density can be written as in this two form, rho h equals to alpha into rho g plus 1 minus alpha into rho f, 1 by rho h equals to x by rho g plus 1 minus x by rho f, right. Now, in the similar fashion, viscosity of the fluid can also be defined. You see, I have shown two important viscosity correlations, McAdams correlation and Chichity correlation over here. So, viscosity can be obtained by several correlations, just like here I have mentioned McAdams correlation, which is nothing but homogeneous viscosity 1 by mu h is equals to x quality by mu g gaseous phase viscosity plus 1 minus x divided by mu f, which is the liquid phase viscosity. Similarly, Chichity correlation also gives you observations. So, mu h is equals to x into mu g plus 1 minus x into mu f. So, in this way we can obtain the viscosity for homogeneous phase. Now, these are correlations because as we have developed over here the densities, homogeneous densities, finding out homogeneous viscosity is not easy. So, we have to rely on the correlations. Okay. Next, let us try to find out how the pressure drop in a homogeneous pipeline can be found out. So, here I have shown you a typical example of a small cross section of the pipeline. So, in this pipeline you can find out the length of the pipeline is dz, okay. The diameter of the pipeline, let us say, that is capital D. So, the perimeter of the pipeline will be P, which is pi into D, and we have considered that homogeneous flow is from bottom to top, okay. As the flow is from bottom to top, in the wall of the pipeline there will be shear stress tau W. Now, let us try to first figure out that how different fluid mechanics equation works over here. So, first the continuity equation you can see over here, continuity equation is A into rho h into UH. So, your A into UH, that is the volumetric flux, multiplied by rho h, which is the homogeneous density, that will be the mass flow rate, which will be constant as per the continuity equation. Next, the momentum equation from fluid mechanics, let us try to write down over here. So, minus del P del Z minus dP dZ is the pressure drop across the pipeline, that will be caused due to three different reasons. First one is friction. So, minus dP dZ due to friction, then minus dP dZ due to Z, which is nothing but the potential head, and then finally minus dP dZ due to acceleration, because flow is there. So, there can be acceleration. So, pressure drop can be caused due to acceleration also. So, all these three, friction, buoyancy and acceleration, all these three are actually giving you the overall pressure drop in the pipeline. Let us now try to see all these individual terms separately. So, first the friction comes into picture. So, you see over here del P del Z friction, that I can write down as 1 by A, which is A is nothing but the area, cross sectional area of the pipeline, multiplied by dF dZ, where F is the frictional force. So, the frictional force I can write down 1 by A dF by dZ. Now, let us try to see how we can simplify that frictional force over here. So, we will be using the pipe cross section whatever I have shown in the slide. So, we find out that minus dP dZ due to friction, this is actually 1 by A dF dZ, right. So, this F is nothing but the frictional force, A is the area, okay. Now, F is the frictional force, and I know that frictional force will be depending on the shear stress. So, I can write down dF dZ is actually your shear stress multiplied by the perimeter P. Perimeter P I have already shown you in the figure, which is nothing but pi into D, where D is the diameter of the tube. So, what I can do, I can replace this one over here. So, we get 1 by A into tau W into P, right. Now, what is tau W? Shear stress. We know from fluid mechanics that tau W we can write down as half rho h UH whole square into friction factor FH. Okay. So, this friction factor is homogeneous friction factor, along with this we are having rho h into UH square multiplied with half, right. Now, how to find out this friction factor? Now, for this friction factor definitely we need to first identify our homogeneous flow is in which regime, whether it is laminar or it is turbulent. So, what we do, we find out first the Reynolds number for the homogeneous flow, which is nothing but GD by mu h. Okay. So, you can find out that from the homogeneous, whether it is laminar or turbulent, depending on that we will be first finding out the Reynolds number over here, which is GD by mu h. Mu h already we have shown, you can take either McAdams correlation or Chichity correlation. Now, after finding out this REH, if you find out this is becoming laminar regime, so what we will be doing, we will be using fluid mechanics equation 64 by RE, which is very common, and if it is turbulent we will be using FH is equals to 0.079 REH to the power minus 1/4. So, once you know the value of REH, finding out friction factor will not be difficult, right. Next, once we know this friction factor value over here, we will be putting this one over here. So, 1 by A into half rho h UH square into FH, right. So, this becomes 1 by 2A into FH. Now, in place of rho h UH square, let us write down rho h square UH square divided by rho h, right. So, subsequently we get FH divided by 2A. Now, this rho h into UH, which is actually your G. So, we can write down this one as G. So, you see over here we are having, by the way I have missed over here the P. So, let us keep also P over here. So, we will be finding out that this becomes G square by rho h having P over here. Now, P by A, so P is the perimeter, pi d, and A is pi d square by 4. If it cancels, we will be getting d by 4. So, we will be getting FH and then 4 by d, okay, and G square, and rho h we can write as small Vh, which is nothing but specific volume for the homogeneous flow. So, here you see we are getting 2 Fh by d into G square, and Vh can be written as alpha into Vg plus 1 minus alpha into Vf, right. So, this is the final equation for the frictional pressure drop we get, which I have shown you over here. You see 2 Fh G square Vf plus x into Vfg. By the way, this part what I have done, alpha I have taken common. So, this will become Vf plus x into Vfg divided by d, d is the diameter of the tube, right. Next, let us go to the next component, which is nothing but the acceleration component. So, here we see that acceleration component will be 1 by A, so per unit area, and this is the momentum W into UH. W is the mass flow rate and UH is the homogeneous velocity. So, rate of change of momentum divided by area, that will be your force. So, let us find out how we can simplify these equations. Next, let us go for acceleration part, pressure drop due to acceleration. So, there we will find out minus dp dz due to acceleration, which is nothing but 1 by A ddz of W into UH, right. Now, you see this W will not be changing with respect to your Z. So, we will be finding out that W by A ddz of UH, okay. So, we can write down this one also, W by A is nothing but G. So, ddz of UH, right. Now, UH, once again let us try to convert it into mass flow rate, because we can have occurrences where pipe diameter is not constant. So, let us try to convert this one into ddz. Now, UH we can write down as W by A into your rho H. Okay. So, this is once again coming from continuity, because we know W is equals to A into rho H into UH. So, let us try to find out what is this differentiation is becoming. So, here we will be calling this one as first factor, and 1 by rho H, which is nothing but VH, small VH, your specific volume for the homogeneous flow, will be calling as second factor. Now, let us see how this by parts differentiation goes. So, first let us keep this one out, and ddz of VH plus we are having G VH and then ddz of W by A, right. W once again is not going to change, so that can come out. So, it will be becoming ddz of 1 by A, right. So, let us take these things separately. So, this is G square ddz of VH plus here I am getting G VH W and then ddz of 1 by A, that will become minus 1 by A square, right. So, W by A, 1 A I can take from here, I can convert into G square. So, this will become G square ddz of VH plus this will become G square by A, we can convert this one to minus, okay, VH into, by the way I have missed over here dA dz. So, here we will be having G square by A VH into dA dz, right. So, we are having two terms over here. First one is actually giving you, if you are having some change of area, then dA dz will be coming over here, and next one we are having ddz of VH, which is the homogeneous specific volume. So, let us now try to see how this ddz of VH comes out to be. So, let me do it over here. So, this ddz of VH, which is nothing but ddz of VH, we can write down as Vf plus of alpha into Vfg. Okay. So, all these things are actually function of P. So, what we will be doing dP dz and then ddP of Vf plus alpha into Vfg, right. So, let us try to do the differentiation first. So, what we will be finding out over here, that dP dz multiplied by, so here also we have to do by parts. So, we will be finding out that, okay, by the way this will be I think in terms of x, not in terms of alpha. Okay. So, we will first write down dVf dP plus here we are having by parts. So, ddP of x Vfg plus ddP of Vfg into x. Okay. So, let us proceed further over here. So, this becomes dP dz over here dVp dVf dP, and here you see once again you will be getting x into ddP of Vf minus of x into dVg by dP plus dx dP into Vfg. So, what I have done essentially, this term I have written over here, dVfg I have subtracted like this. So, ultimately we will be getting dP dz, and here you see this we can take common. So, we can write down we can write down 1 minus x into dVf dP plus x into dVg dP and plus finally this is actually del p del z multiplied by del x del p. So, this will become del x del z into Vfg, right. So, all these terms simultaneously I can put in the equation of the pressure drop, overall pressure drop. Apart from that, in the equation we are also having minus dP dz for potential head. So, that for an inclined tube to be generalized I can write down as rho h g sin theta, where theta is the inclination with the horizontal. So, what you can do, this we can write down as g sin theta by Vh. So, all these three terms, this one and finally this one and the previous one friction factor whatever we have seen, if we club together, then finally you will be getting equation like this. You see, this is the final equation of dP dz for acceleration and this is your dP dz for potential head, okay, gravity head, and finally if we club this one along with frictional head like this, we will be finally obtaining minus dP dz as this equation. So, this one is coming from friction, these two terms are coming from your acceleration head, this one is coming from your gravitational head, and finally in the downside we are getting 1 plus g square into x into dVg dP plus of 1 minus x into dVf dP. Okay. Now, for most of the fluids you can find out, especially for air and water, you can find out that this term whatever we are having in this brace is actually nearly equal to 0. So, we can see that if we cancel this one, then we will be having minus dP dz equals to this term. Okay. Now, if we consider inside a pipeline, now for a pipeline which is a constant cross section, you will be finding out dA by dz is equals to 0. So, this term also we can drop. So, for a pipeline flow having common fluids like air and water, you can find out minus dP dz will be frictional head plus your accelerational head and finally the buoyancy head or gravitational pressure head over here. Okay. So, this is the equation what we can find out for a uniform cross section tube, minus dP dz is equals to 2 Fh g square by d into Vf plus x into Vfg plus g square into Vfg into dx by dz plus g sin theta divided by Vf plus x into Vfg. This is basically your Vh whatever I have shown in the calculations over here. Now, let us try to see if we are having uniformly heated tube, that means there can be situations where phase change is occurring due to the constant heat input along the pipe periphery. So, here we have shown these arrows are actually for heat input. So, as a result you can find out x is changing from 0 to some arbitrary value, let us say x. Okay, and the pipeline length in that domain is changing from z equals to 0 to z equals to L. So, for this type of situations what we need to do, if we have to find out the pressure drop in the pipe, P plus del P to P. So, del P is the pressure drop. So, you can find out we need to integrate this equation for this total length of the pipeline. So, let us do that and find out how the pressure drop can be obtained. So, in this equation I will take term by term and let us see that how dP dz is changing. So, first I will be taking this frictional part. So, we are having 2 Fh into g square divided by d and then we are having Vf plus x into Vfg. So, this we have got as frictional part. Okay. Now, so this is minus dP dz for frictional. So, this if I have to integrate for the whole pipeline, so what I will be doing integration of 0 to z or 0 to L, L is the pipeline, let us say this is for dz, right. So, similarly we need to integrate this side. So, 0 to L and here we are having dz over here, right. So, if I try to integrate, then I will be finding out few terms will be coming out quickly. So, g square by d, this can come out. Now, here we are having function of x. So, what we can do, dz by dx we can take out with the limit 0 to L, and here we can keep the integration with respect to x, and the limits will be from 0 to x, right. So, if we integrate, so this will be 2 into fh g square by d, and here dz dx from 0 to L I can write down L minus 0 by x minus 0. So, L by x, and here this will become Vfx plus x square by 2 into Vfg, right. So, I get finally 2 into Fh g square L d into x I can subtract over here. So, Vf plus x by 2 Vfg. So, this comes from the frictional pressure drop. You can see over here, this I have shown 2 into Fh g square L by d into Vf plus x by 2 into Vfg. So, this is coming by integrating this term with respect to z from 0 to L. Okay. Similar thing we can do for the rest terms also. So, you can see g square Vfg, and we are having dx dz. If we integrate from 0 to L with respect to dz, so we will be getting x only. So, we are getting over here x, and this term g sin theta Vf plus x by Vfg, if we integrate, then we will be getting this term. So, this is a situation where we are having gravitational pressure drop with respect to the phase change whenever present, right. So, this is the final one whatever we get for pressure drop inside a pipeline which is uniformly heated, right. Next, let us try to see or solve a problem. So, here the problem statement is like this: a horizontal tube of 1 centimeter diameter. So, this diameter is 1 centimeter. So, 10 millimeter over here, and 2.5 meter length. So, length is 2.5 meter, contains liquid vapor mixture at 70 bar. So, pressure is 70 bar. Flow rate through the tube is 0.12 kg per second. So, 0.12 kg per second is the overall flow rate W over here. The tube is uniformly heated circumferentially. So, we are giving the heat from circumference, okay, with a heat flux of 100 kilowatt. So, this heat flux whatever you are giving, that is 100 kilowatt. You have to find out the pressure drop if the flow is dry saturated at the inlet. So, at the inlet we are having x equals to 0. So, let us try to solve this problem. So, first let us find out the at pressure equals to 70 bar what are the properties. So, we can find out from water that water table or steam table that T sat equals to 285.7 degrees centigrade, mu f comes out to be 95.6 into 10 to the power minus 6, mu g is 19 into 10 to the power minus 6. Vf is 1.351 into 10 to the power minus 3, Vg is 0.002753, and enthalpy is 1267 kilojoule per kg for liquid, and for gas 2772 kilojoule per kg, right. Now, first let us find out the superficial velocity g, which is W by A. So, W is given, A we can find out because tube diameter is given. So, we can find out the superficial velocity comes out to be 1528 kg per meter square second. Now, let us see what is the enthalpy change happening. So, as we know the mass flow rate W, so and what amount of heat is given. So, we can find out that change of enthalpy delta I will be Q by W, both Q and W is given. So, we can find out delta I is nothing but 8.33 into 10 to the power 5 joule per kg. Now, this heat is actually being absorbed for change of phase. So, we can find out that quality at the exit will be this delta I divided by IFG subtraction between these two. So, we can get at the exit this will be the quality. So, it is starting from 0 and it is ending at 0.553. Let us now try to find out the Reynolds number at the inlet and exit. So, at the inlet Reynolds number will be GD by mu f. So, this becomes this one which is turbulent. So, as per understanding what we have to do for finding out friction factor, we have to follow f equals to 0.079 into REH to the power minus 1/4, and the friction factor comes out to be 3.95 into 10 to the power minus 3 at the inlet. Similarly, at the exit we can find out mu h is equals to 2.96 into 10 to the power minus 5. For this we have used Macadam's formulation whatever I have told you. using the value of x and mu h and mu g, we can find out this mu h. So, at exit Reynolds number will become G d by mu h, which is using this value I can find out 5.16 into 10 to the power 5. This is also coming in turbulent regime obviously. So, we can find out friction factor using same formulations, and it comes out to be 2.95 into 10 to the power minus 3. So, once we get both the friction factors, it is very easy to find out the average friction factor, which is nothing but F h equals to half of F exit plus F in. This comes out to be 3.45 into 10 to the power minus 3. Now, already we have described in the previous few slides that what will be the frictional pressure drop. We know that frictional pressure drop will be 2 F h into g square L by d into V f plus x by 2 into V f g. All the values we have already derived. F h is this one. So, we can find out that due to friction 34.6 kilonewton per meter square pressure drop will be there. On a similar note, acceleration pressure drop will be g square into V f g into x. X we know at the exit, so we can find out this will be coming out to be 33.8 kilonewton per meter square, and as the pipeline is horizontal, there will be no pressure drop due to the gravitational head. So, del p z equals to 0 because theta is 0, right. So, if we add these things, total overall pressure drop will be 68.4 kilonewton per meter square. Okay. So, in this way we can find out pressure drop inside a pipe which is uniformly heated. Okay. To summarize, so what we have done, we have discussed the model equation for homogeneous flow over here. We have also shown you how to calculate the pressure drop in case of phase change, in case of variable cross section, heated tube. Okay. We have also seen some calculation procedure for laminar and turbulent regime, how to find out the frictional pressure drop for laminar and turbulent regime, that also we have seen. Last, to test your understanding at the end of this lecture, let us take some questions. So, first one, necessary assumptions for homogeneous flow, whether it is u g greater than u f, u g equals to u f, u g less than u f, and rho g equals to rho f. So, obviously all of us are getting the answer. The correct answer is u g equals to u f. Second question, homogeneous models are suitable for annular and slug flow, bubbly and wispy annular flow, slug and bubbly flow, and finally char and turbulent flow. So, which one is the answer? The applicability of the homogeneous flow is for bubbly and wispy annular flow. Let us see the third question. For turbulent flow inside a pipe, friction factor is given as, so 4 different equations we have given for turbulent flow. So, which one is the correct answer? All of us know from the fluid mechanics knowledge. So, correct answer is F h equals to 0.079 divided by R h to the power 1 by 4th. Okay. So, with this knowledge we will be ending this lecture. See you in the next one. Thank you.